Hi, everyone. Welcome today to our webinar, Adversarial ML, How Artificial Intelligence is Enabling Cyber Resilience. My name is Mike Slawinski. I'm a staff data scientist here at BlackBerry Cylance. I work on our flagship product, Protect. I also work on a fair amount of adversarial modeling, as well as some behavioral sequence modeling. And today I'll be presenting with my colleague, Josh Fu. Josh, if you'd like to introduce yourself.
Sure thing. Thank you very much. Very nice to meet all of you. Like he said, my name is Josh, and I'm a security engineer here at Cylance. And over the past year, I've been speaking at various conferences and really work on talking to customers about what Cylance actually does and how it's able to help them with their security postures.
Great. Thank you, Josh. The agenda. So first, I'm going to talk a little bit about file classification via machine learning. I'll then talk about some of the weaknesses that arise in these kinds of models. And then I'll go into how these weaknesses can be exploited to make a malicious file look benign. Okay. And then finally, I'll go into different ways of how you can harden your model against these kinds of adversarial attacks. And then for the latter half of the presentation, Josh will talk about some practical applications of these things. Okay, so what do we ultimately want to do? We want to construct a scalable classifier for determining whether or not a file is benign or malicious. Okay, so these files can include anything like a script, usually a portable executable, Word document, PDF, and so on. So many security vendors, including us, have large corpora of labeled data sets. And so we visualize this on the right, where the little virus graphic guys represent our malware. And then on the lower right, we have our familiar benign files, okay? And what we do is we take this large corpus of files, labeled files, and build a classifier, right? So this is a machine learning model, which can, the purpose of which is to classify a new previously unseen file as either benign or malicious. And the main topic of this webinar is, well, how can these classifiers be attacked? Okay, so the visual that I want everyone to keep in mind is this little movement on the lower left, where I'm taking a malicious file and I'm moving it across our decision boundary so that the model thinks that this file is benign, even though it's still malicious. Okay, so we're indicating that it's a little virus, but it now has the little I'm a good guy halo over its head. Okay. And so really what we're asking is it possible to perturb a file, that is, change a file in a small way, in such a way that it crosses our decision boundary, fooling the model? Now, there's one theme that I want everyone to keep in mind throughout the talk, and that is that naivete is dangerous. Okay, so what we often do is we make, in machine learning, is we make the mistake of assuming that the model is judging an object just as we judge it. Okay, so in other words, we assume the machine learning model has baked into it a conceptual understanding of the objects being classified. Okay, so what does that mean? Well, let's think of a specific example. So imagine a lie detector. Okay, so the question is, what is a lie? So and the analog here is what is maliciousness when it comes to files? So from the human point of view, a lie is a statement believed to be false, but offered as true. Okay, but then when we look at the lie detector, we have a paradigm shift. Okay, so to the lie detector, a lie is the heart rate above a certain threshold, perspiration above a threshold, body movement above a threshold. Okay, so the point here is that if we want to trick our lie detector, that is our lie classifier, we don't have to alter our statement in any way necessarily. We don't have to make any fundamental changes to our statement that we're trying to offer as true. All we have to do is adjust these numbers, okay? And the analog with, in the file case, is that we don't necessarily have to take the maliciousness out of a file. We just have to adjust the features that our model cares about. So what is machine learning? So let me just give you guys a quick overview. So the definition I like is that it's the design and implementation of learning algorithms. Okay, so what is a learning algorithm? So these are just algorithms which are not explicitly programmed. So the idea here is that the decision-making scheme is a result of optimizing some objective function, some objective, let's just say, based on observed data. Now, what is the utility of these kinds of algorithms? So why are they necessary? Oftentimes data, including our file data, has the following property. So that we have extreme data variability resulting in a possibly infinite signature set. Right, so file classification really involved writing signatures. So you would handwrite some number of signatures, and if the file exhibited some characteristic which triggered the signature, it would be classified as, say, malicious. Okay, but the problem is this extreme data variability. So for a simple example, imagine that we have hand-drawn squares, or even imagine that we have hand-drawn squares from children. Okay. And we want a classifier to say, is this a hand-drawn square or is it not? Now, the two squares on the left, the two shapes on the left, you can probably infer that those look mostly like squares, while the one on the right is not so much. Okay, now if we had perfectly computer-generated squares, it would be easier to write a signature-like algorithm to determine whether or not this object was a square or not. You'd say, the algorithm would check, are all these pixels perfectly aligned? Are there four corners? Are they perfectly 90 degrees? But in the case that they're hand-drawn, you can imagine kind of an adversarial perturbation that you could make, which would break all of your signatures, or even one. Right? So a small little perturbation on any edge, this thing may still appear as a square to us, but would break a signature-like algorithm. So the idea of a learning algorithm is to take many examples of these drawings. So many examples of what we would call hand-drawn squares, many examples of shapes that we would not call hand-drawn squares, and design an algorithm which would infer what we mean by a hand-drawn square and what we mean by something that isn't. Okay, so that's the idea, is letting our algorithms determine what the important features are. Okay. So what we have here is a graphic showing the process of learning by a machine learning algorithm. Okay, so what we want to picture here is the red dots. Let's focus on the picture on the left. The red dots representing malware, the blue dots representing benign files. And as training moves along, as we encounter more and more examples, as we update our model parameters, we see this nonlinear decision boundary forming. Okay. So as I said, as we encounter more examples, as we let training progress further and further, this algorithm begins to learn through this decision boundary what is benign, what is malicious. Now, certainly the real model has many more dimensions than just the two displayed here, but that's just for the sake of pedagogy, really. But even when we visualize this sort of thing, we're looking at a picture as on the left, where the model is really just looking at our files in some kind of feature space and adjusting this decision boundary so that when we encounter a new file, if it falls, say, above the decision boundary, we'll call it benign, referencing this picture. If it falls below the decision boundary, we'll call it malicious. And what's interesting about neural networks, just as an interesting note, looking at the graphic on the right, you can view this nonlinear classifier as a linear classifier on the final layer of the neural network. And that's what we see on the right. And that's not too important. It's just if you have a familiarity with neural networks, it's an interesting point of view beyond what we see on the left. Okay. So now let's assume we have a trained model. So we're looking at our picture here on the left, where the red dots represent our malicious files, the blue dots represent our benign files, and the model is really represented by this nonlinear decision boundary. Okay, so again, we classify a new sample as benign or malicious depending on which side of the decision boundary it falls. Okay, so let's zoom in on a certain part of this decision boundary. Let's look on the kind of the upper right part. So if we zoom in, we see our decision boundary in blue and our malicious files represented as red dots on the right and benign files represented by blue dots on the left. What an adversary might be able to do is take a malicious file, something like a ransomware, and make minor adjustments to that file in such a way that when the file is classified by the classifier, it now thinks this file is benign, even though the control flow, the actual functionality of the file, remains unchanged. And so that's what we're seeing on the lower right here. So functionally, that is, the control flow of the file, its malicious behavior, persists through this perturbation. But from the point of view of the model, it's now benign. And so remember back to that lie detector example, right? So this is a case where we don't have to actually change anything fundamental about the file. We're simply finding features which are susceptible to adversarial attacks in the sense that they can be altered without changing the fundamental nature of the object being classified, whether it's a lie or whether it's a file or whether it's an image. Okay, so to make this a bit more concrete, let's look at a very classical example from one of my favorite papers from 2014, where this adversarial attack, these adversarial examples were constructed for images. Okay? So what we're starting with is an image classifier, which is classifying images of animals. Okay? So we can start with an image of a panda, and we can add specially designed adversarial noise to this image in such a way that we humans still see this image as a panda, but that the machine learning classifier that was trained on many examples of pandas and dogs and cats and whatever else, that classifier is now tricked into thinking this image is a gibbet. Okay? And we see, again, this abstract picture on the right, where we have our decision boundary, our image as represented by our red dot in feature space being moved across this decision boundary. Now, what's important for us is that this sort of thing can be done to files. The analog I'm drawing is with this red box. So rather than adding image noise, rather than just adding white noise to this, specially designed white noise to this image, we're altering something in the file which won't affect control flow, just for example. So let's say maybe we're looking at the header. Maybe there are some strings in the header which we can change, which would allow the file to keep its same control flow, but which might trick the classifier, right? So very often, classifiers in general, and especially machine learning classifiers in security, are picking up features which are not fundamental to the control flow of the file. Okay? And these are the dangerous features. Okay? So analogously to the image on the upper right, we're looking at the lower right, where we're taking our malware, whether it's ransomware or whatever else, we're making these adjustments to non-fundamental features and tricking the classifier by moving it across this decision boundary. Okay, so this is one of my favorite slides. So let's kind of take a step back and try to understand why these kinds of adversarial attacks are possible. So this is an actual example that I read about a few years ago. So somebody tried to create a classifier which could classify an image as either a wolf or just as a common dog that you would have as a pet. Okay. Now, what you'll notice, and this is indicative of what happened for the entire corpus, all of the wolf pictures had snow in the background. Okay. So that's these white pixels representing the snow were co-occurring with these images of the wolf, right? Now, certainly wolves have evolved to live in snow, but in terms of the actual form of the wolf, there's nothing intrinsic to that having to do with white pixels, right? So what can happen is that the model, because it doesn't see these images the way we do, it can pick up, it can focus in on these co-occurrence features. In this case, the white pixels, the snow pixels. So an adversary could easily trick this classifier by taking a picture of your ordinary house dog, this little Chihuahua, including snow pixels in the image, and this would absolutely trick this classifier, because the classifier has learned to pick up on these co-occurrence features. And the same thing can happen with malware. Right? So again, when we think of malware, we think of encrypting files in terms of at a higher level in terms of ransomware, or a malware that's opening up a network connection and giving control to a command control server or something. But in terms of the model, there can be plenty of these features that show up in files which simply co-occur with malware and aren't fundamental to anything intrinsically malicious. So again, snow features, these are model features which are not fundamental to the nature of the object being classified, but which aid in classification due to co-occurrence, just like the snow features, the white pixels representing the snow in the wolf-dog classifier. So models trained on such features are vulnerable to adversarial attacks. Okay, and the key takeaway, as I mentioned on the last slide, is that malicious and benign files have these snow features too. Okay, so these can manifest in the form of strings, header information, file size, and so on. Again, features which co-occur with that class, whether the class is benign or malicious, but which don't necessarily have anything to do with the fundamental nature of the file, that is, its control flow. So what do we here at Cylance do to protect against these kinds of attacks? Okay, what makes our classifier different from those from our competitors' classifiers, even those classifiers that advertise very high accuracy? Right? High accuracy classifiers can still be very vulnerable to adversarial attacks. Okay, so the first thing that can be done is reduce the leveraging of these snow features. Okay, so another way to put that is that these are features which, when perturbed, change the nature of the original file. So unlike these string features, which you can just delete a character or add strings or subtract strings without changing the control flow of the file. Okay, we want to reduce the number of features that we have which are of that nature. We can also adversarial train. So all I have here is leverage more sophisticated learning algorithms, but what that really means is adding an adversarial training regularizer to the objective function, so to the loss function, which allows the model to take into account the possibility of these kinds of attacks. One of my favorite methods is anomaly detection. So what we can do is learn a probability distribution of the training set, the files in our original corpus, represented by that little graphic at the beginning. Learn a probability distribution of these files so that files altered to trick the classifier will look strange. They'll be assigned a very low probability, right? So while that file, when altered, may trick the classifier, it will be altered in a way that makes that file look very out of the ordinary, okay? And when that file is assigned a low probability, we can make a decision that we can say, well, sure, the classifier says this is now benign, but it looks very strange. So let's err on the side of caution and classify it as malicious. Okay. We can also include adversarial examples in training. Okay. So one thing we can do is in-house construct as many of these adversarial examples as possible and add those, so we can make these perturbations ourselves and add that back into the training corpus, and then train our model on the corpus, which includes these adversarial examples, allowing it to learn what these adversarial examples may look like, adjust the decision boundary, keep our high accuracy, and harden our model at the same time. Okay, so with that, I'm going to pass it off to Josh to talk about some practical applications of these things.
All right, thank you very much. When we look at the practical applications of these mathematical concepts that Michael is talking about, some of the key areas have really been in image recognition, specifically CAPTCHAs. So CAPTCHAs were originally created for two purposes. The first was to prevent bots from adding URLs to AltaVista's search engine. And the second was to distinguish humans from computers. And this is because at the time in the early 2000s, it was very hard for a computer to be able to read and write text. And an incredible result of this effort was the digitization of millions of books and the New York Times. Since then, other types of CAPTCHAs have been created to continually make people prove they are actually humans. And the reason why Turing test is in the name CAPTCHA is because of Alan Turing, who is a British genius and one of the godfathers of computer science and artificial intelligence. In addition to being a key figure in breaking the German enigma in World War II, he devised the Turing test in 1950. The purpose of this was for an examiner to see if a human was distinguishable from a robot. In addition to his creations, he also predicted that by the year 2000, machines with only 100 megabytes of storage would be able to pass this test. He was correct in that computers would eventually be able to pass these tests. The type of neural networks used for recognition is a convolution neural network, or CNNs. What it is doing is assigning each feature or characteristic of the object a number in a process called vectorization. Those get calculated through each layer until we get a number that is the answer that equals something like 42, or in this case, cat. The fact is that neural networks can be used for malicious purposes too, such as reading and then creating clickbait. An example of this is exactly what these two researchers, John Seymour and Philip Tully at ZeroFox, did in 2016. What they did was they created a Twitter bot that was able to understand what people were clicking on so that they could then scrape those titles and scrape those subjects and then create clickbait that was clicked on as often as what human hackers were able to create. And on the flip side, there was another type of attack, not created by these gentlemen, but called laser phishing. What that does is it takes the way that people actually write, because everyone uses different grammar, they use different cadences, they use different punctuation, and be able to mimic the way that they actually write messages in order to sound like them when they're sending out these messages that are completely created by bots. And this uses another area called natural language processing, which is the reading and writing of text. So this is where we can see this being affected in non-image ways. And this means that CAPTCHAs are vulnerable to attack, as multiple researchers have proven in recent years. In fact, one way that is being done in the real world for free is completely approved by Google. And this is one of the ways is called Browser or Buster, which is a browser extension that you can use in Chrome. And it's called CAPTCHA Solver by Humans, and it's by Armin Sebastian. You can go there now. And what it does is it uses Google's own natural language processing computing power up in the cloud in order to bypass its own security. And this is because on every Google image CAPTCHA, there's an audio component for people who are blind. And what this browser does is it takes that audio, instead of looking at the image, and puts that up through Google's own API and processes it by turning that audio into speech and then to text, and then putting it back into that field so that then the verify button will see that, hey, this is indeed a human, or believes it's a human, and allows you to then go past this CAPTCHA. And this is really the state of security today, where you can use someone's own technology to bypass their own security. And for the truly lazy or non-technical folks, you can also go to Google and just find CAPTCHA breaking as a service companies that operate for as low as 1/100th of a nickel per CAPTCHA. You can even rate those CAPTCHA breakers, just like your Uber driver. And this is where adversarial protection using noise, as Michael discussed earlier in the Panda example, can come into play. As he mentioned before, tiny perturbations in the pixels of an image are enough to trick the classifier. In this example, the researcher was able to algorithmically make this image with Elon Musk in it be classified as a bookcase. The reason why he could do this is because each pixel had 250 color units on the scale, with the researcher limiting the changes to just 3 units. In the end, the algorithm rarely made any changes beyond 1 unit. And at this time, this fast gradient step method is the simplest and most efficient method to carry out this task. And this method works because it helps find the minimal perturbation to maximize the error. And the noise image on the far right is only amplified and has colorization for the presentation purposes. Otherwise, it would actually only be a grayscale box. And while considered an adversarial technique, this can enable resilience as well, in order to fool attackers who would try and bypass an image using a bot to correctly identify the image using their own classifier. And while it looks imperceptibly identical to the human eye, it is completely different digitally. And this concept of adding noise to an output can also be applied wherever someone is trying to bypass a protection mechanism. As Michael mentioned on his last slide, one of the possible defenses is including adversarial examples in your training set so your model has awareness of these types of examples. So what are some of the key takeaways from this presentation? One is when focusing on usage, tools can be easily available and cheap. And machine learning is absolutely going to have a role in the arms race because it's already being used for customers to defend themselves. And because of that, attackers are absolutely going to find ways around it. And we believe that the next frontier for machine learning is going to be solving identity and authentication challenges, and this has already begun. And if you're wondering how machine learning applies to Cylance, we do this in multiple ways. So we use machine learning to recognize files, and we do this with our solutions Cylance Protect for enterprise and Smart AV for the consumer. So you can use this to protect your personal machines and your family's machines. Recognition of processes. This is optics, Cylance Optics. And then recognition of people. This is what's going to be coming. And this is how we're going to be solving that identity challenge. And this will be Cylance Persona. And additional benefits that we're able to use is even using this with offline systems and old systems that can't really be updated. It enables you all and our team to do faster threat hunting, and Protect also works against flawless attacks and scripts. But we have an entire consulting arm which uses this for incident response, compromise assessments, mergers and acquisitions, and also anything else that you all as a team may want to be using it for. So if you are interested in looking at how Cylance works and how it can protect your organization, click on Get a Demo in order to see what we can do for you. And for anyone who wants to learn more, we included these links in this presentation, so you can go and look at this, take a screenshot, and go and look for yourselves on how we can help you with your learning, and also for your own learning, look at these different articles as well. You can connect with us at Cylance Inc. or J4 Security, and you can also look at what Michael's been up to on his GitHub page at github.com, Gtown Rocks. So with that, we'll leave the remaining time for questions and answers. All right, so the first one is, do you go to the dark web to buy malware, then either train with it or test with it? Michael, are you able to speak to the corpus?
The malicious files are moved into the cloud through detections. So basically, if the classifier classifies some files as malicious, then it's moved up into the cloud.
Perfect. And I also do want to add to that in terms of where we do get our corpus from. So in addition to the detections that we find, we also use areas such as VirusTotal, but we don't rely on it because that does require additional classification. And we do also have a data sourcing team that gets it from additional sources that they have and also on creation. So some of it is a proprietary mix in addition to getting it from detections. And then one of the other aspects is making sure that is classified correctly. Second question is there any date for launching Cylance Persona? So from a beta perspective, it is available a little bit sooner, depending on the criteria, but the launch date should be at the end of winter this year, going into spring. And then next question is, some updates on the Cylance mobile for Android and iOS, please. So while I can't give a hard date on when that will be, we are looking to release initially an Android protection later in the year, if not early next year, and then iOS after that. How Cylance keeps itself ahead of competition machine learning? Michael, would you be able to answer that one?
Sure. So we have a quite a large and experienced data science team. We exist so that we can accomplish that task. I guess I would answer it in a general way that it's our approach is as in any other industry. I mean, we have top researchers here. We publish pretty frequently You can go on Archive, or I'm sure any top security, machine learning security journal that you can find, and you'll see authors from our team. I mean, in addition, it's really about leveraging not only our machine learning expertise, but really leveraging the vast amount of industry knowledge we have in-house. So we have quite a few people who are, you could describe as former hackers, security professionals from all over the world. So to me, it's really about combining the mathematical point of view, the machine learning point of view, with the industry expertise that we have here in-house.
Yeah, I completely agree with that. And also, I would also just like to add the fact that, like what Michael said, we have people in-house who not only understand what the industry has, but also who are just constantly trying to break it and bypass it themselves. And when we do find areas where the machine learning can be improved, we absolutely add that in, because we want to not only have the best solution there that's machine learning based, but we want to continue to have that. And that's exactly why we have those people who are in-house and are able to find those areas to improve in. Good question. So I don't see any other questions in the chat. So let's see, one more. Let's see, Cylance Smart AV can do behavior analysis on files or process that get through the classifier.
Sorry, that sounded sort of like a statement to me, or was it? It was a question as to whether the product can do that.
I'm trying to interpret it as that. I think maybe can.
Yeah,
maybe it's the question of, can Smart AV do behavior analysis or process?
Oh, I see. Sure. So the protect model is a static classifier. So that classifier parses the file, it vectorizes it, and then it classifies it as either benign or malicious. It's not actually running Cylance optics as well as Persona. Once Persona becomes online, the focus of that product is more the behavioral aspects of interacting with the machine, whether it's a person or a file.
And one thing to note, if you do go to our website, I believe shop.cylance.com, you can get a trial of Cylance Smart AV for your machines, and we are running a special on it right now. So it can be one-to-one. You can have a license that covers up to 5 devices or 10 devices, and you can look at it for 1 or 2 years. I have it on all of my family's machines now, and they don't call me for help desk calls anymore. All right. Can you speak to the roadmap for Cylance Protect? I would say get a demo, go and click on get a demo, or send us a message and we can have a separate conversation for that one. My Smart AV is so clean. Can it give me more diagnostics so that I know it is running? That one is a roadmap item, because we do want to make sure that customers actually see a few more pop-ups and notifications to make sure it is running. And that actually is one of the areas where we have actually received a lot of feedback, because compared to what they traditionally had, which constantly had pop-ups saying your antivirus is out of date, or it would cause the fans to spin or the computers to heat up or bog down the resources. We don't do that. That's absolutely an area where we are going to be adding that in as a feature. All right. Is Cylance recommended for web servers or file servers? So that it really just depends. I would say send us a message and we can get deeper into the weeds for you based on the type of environment that you have. But the short answer is anywhere where it can work on a host, especially something like a Windows server, then we'll be able to run it. And we have tons of customers that do that without it causing conflicts. All right. Well, if there are no more questions, let's see. Oh, one just came in. I know Raspberry Pi might be a small market, but a good IoT. Would you support it? This is actually a really interesting question, because we are looking to expand our Linux support. And I actually just personally got myself another Raspberry Pi this weekend. As a company, we are getting more into the IoT space, especially with this acquisition by BlackBerry, because they are positioning themselves as a strong leader in the IoT space. So it's definitely within the realm of possibility. And it is something, again, we are looking at to really be able to cover all IoT devices in the future.